And the methods are intuitive and easy to explain. We'll talk about some of them in just a moment. So one of the shortcomings is that these methods are still black box, right? You get these excellent predictions, but it's a challenge to explain what variables are driving the predicted values or driving the model or not. We'll talk about the existing variable importance measures, but as we show below in a couple, in the most prominent cases, the existing variable importance measures either have the wrong null distribution or don't have any clear null distribution at all. At best, the existing variable importance measures in the literature are descriptive and aren't meant for it, and aren't suited to inference, even though people are increasingly using random forests and boosting, they want them to be useful for identifying explanators or connecting explanatory power with predictors, and that just doesn't seem to be the case. And we're going to talk about why, and then take a stab at fixing it. So in the beginning, we should talk about some of the existing methods for measuring how important a variable is in these machine learning methods. The methods that are most commonly used split into one of two different types. The first are permutation methods. This is already implemented in the random forest implementation, and you'll find it in boosting methods. and this is a permutation method. So what you do is you say, here's one of my variables, say x3. I fit the model to all the data, and I capture the mean squared error. Then what I'm going to do is permute the variable x3 and see what that does to the predictive accuracy of my model. And to the extent that manipulating x3, just particularly permuting it up and down, to the extent that doing so makes my model perform worse, I think x3 is a useful explanatory variable. So we attribute the change to x3 for the change, we attribute to x3 the change in predictive accuracy or the change in fit attributable to a model with that variable permuted or not. All right. The second method kind of seems to work, but we're not sure what it is or why it works. But this is implemented. GRF, the Wagner and Athy's random forest package in R, have a variable importance measure that they characterize as a simple weighted sum of how many times feature I was split on at each depth of the forest. And as near as we can tell, and we reserve the right to spend more time looking into this over the next few months, that seems to be how they characterize it. Short of actually going into the code, this is all we know that it is. So as a simple weighted sum, it's never zero, right? Or unless the variable is never selected. But we're not sure what the null distribution is, right? What would a noise variable look like under this measure? So those are sort of, that's this as our reading the lay of the land for.
Can I ask you a quick question regarding that?
Please, please, please.
My intuition would be that a noise variable wouldn't be systematically selected at different depths of these forests because it wouldn't improve the model fit at all.
Oh, absolutely. Except the way the generalized random forest works is they select 5 variables at random and then pick the best one.
Yeah, again, so if it was a noise variable, it wouldn't be the best one.
It could be if 5 of them are all noise variables.
Sure. So if all of your model is noise, then the most important variable in that noise model will also be noise. That doesn't seem like a problem to me.
Oh, no, but say, for example, if you have a giant data set with say 60 features and maybe 30 of them are noise. And it happens that when you run a GRF, 5 of the chosen one among the 30 noise variables, then that could happen.
I mean, it could, but the idea would be it shouldn't if the random draws are you're sampling from your 30 variables often enough, and you're going back to the pool and you're killing off the trees that aren't working very well. I'm not clear why a 0 wouldn't be the right. I'm not sure what we're trying to, I'm not sure what the problem is with this technique, other than maybe it's a little bit difficult to interpret.
I have a question. May I ask you a question?
Please, please.
Let's
Okay.
I think it'll be more productive to unless it's a clarifying question, to just let the presenters continue and
Yes.
hold the questions for later. So Arthur, is it a clarifying question?
No, it's not a clarification question.
Okay, so let's just continue and just we'll hold the questions till after the presentation. Thanks.
So to come back to the first question, and please come back to that in questions and answers, the GRF has a habit of, in the data sets that we use, it tends to select all of the variables at least some point, and we don't get any zero variables when we run it on UCI net data down the line. As to what should happen theoretically, that's still something we're trying to understand. But I'd be glad to talk about that in a few minutes. The motivation for this particular project was a set of data that Noah Foster here in Zenobia gathered as survey experiment in Estonia. And Zenobia just wanted to know which variables were most important in predicting the outcome. So this was Zenobia, this was an MTurk experiment, right? And then you're spiraling it into other ones?
No, it's recruited through Facebook, constructed to match
Oh.
the national census adult population in Estonia.
So thank you. So the outcome here is whether or not the respondent is voting for a particular party. So in this case, if you look at GRF and random forest, this is just a figure of using 12 different of the variable importance measure and 12 different seeds across the same data. So it's given the exact same data each and every time. And we just want to know what's the variance or the fluctuation in the rankings of the variable importance measure. And looking across these, GRF actually seems to do reasonably well in terms of coherency. But coming back to the earlier question, all of the 54 variables, I believe, show up, or 50 some variables show up at least one time out of the 12. The other issue, it's actually reasonably coherent up towards the top, but over here, the inference on it starts to fan out. And your inference can actually depend on which seed you run. Again, this is all on the same data. You see a similar pattern with random forests, although the variance and the rankings are higher under the permutation test. So it's relatively straightforward in the first 4, 5, 6 variables. And then it just sort of fans out into something that doesn't necessarily lead to convincing inference much beyond that. This is our motivation. We're going to talk about some of the methods we have to try and help out in these scenarios. The overarching goal of our method is to develop a method that is comparable in performance and mean squared error relative to GRF and random forests, while still returning a theoretically valid variable importance measure, by which we mean that it has a null distribution centered on 0, or at least we can characterize the null distribution. The setup of this. So we're going to assume observations run from 1 to n, index from 1 to n. Yi is going to be the target or dependent variable that we want to predict. And for this talk, we're just going to focus on mean squared error and the regression problem. Then the covariates xi are going to be a vector of p covariates or features that we're using to predict y. And then xij perm is going to be the ith vector with the jth variable permuted across observations. Okay, so this is going to denote just this xi variable, except the jth variable has been permuted. We're going to use a few different functions in this analysis to characterize what we're doing. The first thing we'll need is a loss function indexed by parameters theta, which just gives us a sense of how close xi is to yi, parameterized by theta. There's the empirical loss function, which is just the average of the loss function over observations. Then there's the risk function, which is the expected value of the loss function. We're going to use 2 more elements. The first, the estimate theta hat, is going to be the minimizer of the empirical loss, however we characterize that. And the population minimizer is going to be the true value that minimizes the risk. All right, hopefully this is reasonably standard type material. So beginning with the variable importance measures, and we're going to talk for a moment about the variable importance, the permutation-based variable importance measures. The way these work is we're going to estimate theta hat on the sample, where theta hat are the parameters of the tree or the forest or the regression or the SVM or the what have you. And we're going to compare the empirical loss under Xi and the empirical loss under the permuted Xij. So the estimated variable importance measure for variable J is going to be the average increase in loss attributable to permuting the jth observation over the observed sample, where the variable importance measure for J is the population analog, based around the true value with n goes to infinity. All right. The larger this variable importance measure is, the more important we estimate the variable to be. So the first question we're asking is, do we want to use a permutation-based approach to measure variable importance? And the answer we assert is no, and we're going to provide a simple example, hopefully with a reasonable intuition as to why. Assume we're going to run a standard linear model with interest in beta 1. And let's assume we just have an outcome variable, 2 covariates, and we just want to run a simple linear regression. So in this case, we get estimates, y hat I, beta hat 0, beta hat 1, and beta hat 2. No interactions, nothing, just a very, very simple model. And the question we're asking is, do we want to compare this model to this model? So the residual sum of squares under this model to the residual sum of squares under this model to figure out how important xi1 is. And that's the question we're asking. And the answer is not quite. We had to think about this for a while. So let me show you how this works again in the simple regression setting. What we're going to do is we're going to define the predicted value of xij, as the predicted value of xij given all the other x's. And then we're going to define the partialed out version of xij as xij minus its predicted value, again giving all the other x's. This concept, and we didn't have time to go into it too much, but this concept is kind of floating around in the literature in some interesting places. But the idea here is that for the jth variable, we're going to partition it into 2 parts. A part that's explained by the other x's and a part that isn't. Those two are obviously mutually exclusive, at least in population. And what our argument boils down to is that if we want to figure out how important variable J is, we only want to manipulate the part of J that's not explained by the other covariates. In one sentence, that's our basic insight. To figure out how important J is, we want to see the effect of permuting it, but we only want to permute the part that's not affected by the other x's. Why is that? Because, and this gets more pronounced in machine learning or high dimensional models, but basically, this x hat ij, if you permute all of xj, you're also permuting some other part of xij that's explained by the other x's. And that's going to mess up other parts of the model, what trees are selected, what splits are selected, that sort of thing. And it's going to lead to a misleading sense of how important the variable is. Mechanically, it's the difference between running a bivariate regression, a bunch of bivariate regressions, and a multivariate regression. We want to partial all the other x's out of the x the covariate we're interested in before we see how important it is. Returning to our simple model with 2 covariates, what our argument is that what we want to compare is y hat I, beta hat 0 with x tilde I1 and x hat I1 and x tilde I2 and x hat I2. So what we're going to do is we're going to take xi and we're going to split it into x tilde and x hat. And we're going to take xi2 and split it into x tilde and x hat. And then we're only going to permute this part of it. So we want to compare the residual sum of squares under this model to the residual sum of squares under that model. All right? Is the point passably clear? Please interrupt if there's a clarifying question. So our process, just in the simple linear regression case, we're going to go to the original data and generate partialed out and predicted x's. We can just do that with a regression. Then we're going to crossfit. We're going to estimate the coefficients on half the data and predict on the other half and get the mean squared error. Then we're going to permute the partialed out variable on the other half and gather the mean squared error. So in this sense, here we get the in-sample mean squared error. Here we get in-sample predicted mean squared error. Here we get the in-sample predicted mean squared error under permutation. We're going to switch the roles of these two and then repeat. Then we're going to compare the cross-fitted mean squared error for the we're going to compare the cross-fitted mean squared error of the permuted part. Compare the cross-fitted mean squared error to the permuted partialed out mean squared error. So to show you what this looks like before we hit the next slide, what we're saying is we're going to take the variables and partition them into predicted and partialed out variables and only permute the partialed out variable to estimate its importance. We're going to compare that to just fitting a linear model on those two variables and permuting one of them. So the simulation that we're going to run, we have 50 observations, 2 variables, okay? The covariates are multivariate normal, they correlate at 0.8. The noise is going to be IID standard normal, just Gaussian noise. And our outcome, our target variable, is going to be yi is xi2 plus epsilon I. So in this setting, xi1 doesn't matter, right? It just doesn't enter. And we want to know, if I fit a regression with x1 and x2 and permute x1, how does it perform in identifying which variables matter? And if I separate into the partial and predicted out, what happens? And you can see the effect here, even in this very, very simple setting. So if I regress the outcome onto x1 and x2 and permute x1, this is the change in mean squared error attributable to x1. So x1 seems to matter across a large number of simulations. It has a positive bias to it. If we only permute the partialed out version of x1, so if we fit our model using the partial and predicted out values, then only permute the partialed out variables, you get something that looks like this, which is actually the median is just slightly below 0. The mean is exactly 0 to 3 decimal places. And you get a null distribution on the variable importance measure that's centered on 0, which is where you'd want it to be. Okay. So what we're going to do is we're going to repeat that process, except instead of linear models, we're going to plug in random forests and boosting steps and things like that. Okay. So we're going to take that last algorithm that we used on the linear model and complexify the algorithm while preserving the basic point. So in this case, we're going to generate predicted and partialed out covariates using the random forest. So we're going to take each of the variables and use a random forest to predict and partial out the covariates given all others. So we have 2 different sets of covariates we're working at. Then we just found it easiest to engage in, to code up a boosting algorithm, which is just an upgraded gradient descent. So what we're going to do is we're going to initialize the residuals as the outcome minus its mean. A step size of eta is 0.1 times the standard dev of y. Then for each iteration, we're going to go through the following process. First, on the full sample, we're going to find the 2 covariates that best model epsilon hat I comma t. We can talk about that in, we can talk about how this works, but for now, we're using an F statistic to figure out which 2 variables work the best. Then we're going to split our sample in half into an auxiliary sample and an estimation sample. And then in the auxiliary sample, from the 2 best covariates, we're going to construct a tree from the predicted values, and then another tree from the partialed out values. And we're going to regress the current residuals on the tree indicators. In the estimated sample, we're going to take the fitted values of the residual on the, we're going to take the fitted values, we're going to use this model to predict down here. And we're going to estimate variable importance by manipulating the partialed out variables and estimating the effect of the partialed out variables on the mean squared error. The next step is we're going to crossfit. So we're going to take these 2 and swap them. So we get an estimated value for each observation. Then we're going to update the residuals and repeat. All right. This was understandably brief, but if there are questions or clarifying questions, please do let us know.
Can you say again what 2.2 is?
The auxiliary sample? Sure. what we're going to do is we're going to learn the tree model on half of it. We're going to generate a prediction off half the data in the auxiliary sample, and then predict it on the other half. So we're never using the same data to learn the tree structure and predict the residual and predict the fitted values. Does that make sense? So we split it's a subsample approach. We take our data, we take half of it, fit these two different trees to it, take the tree structure, and then take that tree structure to predict the outcome on the other half. And then we swap halves. Was that more clear, or wait till questions, or?
My question was about the regressing the current residuals on the tree indicators. I'm just not familiar with that.
Absolutely. So we have a tree in terms of the x hats and a tree in terms of the x tildes. The trees themselves are just the fitted values and sample fitted values from a tree come from, you can represent them as just regressing the outcome on the indicator variables for the terminal nodes. So what we're going to do is we're going to take the indicator variables for the terminal nodes from this tree and the indicator variables from the terminal nodes from this tree, enter them into a regression of the outcome onto those terminal node indicators, and fit a model up in this sample, then use it to predict down here. Did that address the question?
Yeah.
Okay, thank you. What that does is it gives us one tree in terms of the predicted covariates and another one in terms of the partial lab. All right, so how does this perform in terms of mean squared error? Across a variety of different UCINet data sets, we're going to go through two of them now. We do some combination. We generally do better than the random forest algorithm, and we're competitive with GRF on depending on how you measure it, depending on the data set, one to the other. So in this particular study, one thought we had is someone may say, instead of doing your algorithm, why not just put in partialed out and predicted X's into GRF and random forest? And we tried that, and across settings, the mean squared error is actually pretty bad relative to just including the full covariates. So there's not much point we found to doing this, but we tried that first in order to try and save ourselves a lot of coding. This is the random forest mean squared error. And the way we did this is we took the data set, split it in half, fit our algorithm to half, and then at the number of trees or the number of steps, we just recorded the out of sample prediction in the half that was a pure held out set, and went with the model that had the best held out predictive value. Are there ways to improve this? Yes, we're going to talk about those towards the end. As I mentioned, we're still ongoing with this, but very open to ideas. But what you'll notice is that our boosting goes down pretty low. It starts to come back up on this data set, but we find the best value here, which in this example does beat generalized random forests. In the next one, generalized random forests does a little bit better than us. So this is the airfoil self-noise data. We're going to systematically run through UCINet regression problems. Here's the GRF and random forest with the partial and predicted out values. Here's the random forest, here's us, and here's GRF. Across the different data sets we beat random forest just as implemented in R. And depending from data set to data set, do better or worse than GRF across data sets in terms of mean squared error. The Estonia data, this is Zenobia's data, we actually do notably better than random forest and boosting. So again, these are the partialed out ones, which we're probably going to drop at some point or put in an appendix because there's not much point to doing them. And GRF and random forest fluctuate around the same mean squared error, and we come out looking better. Now, I don't want to be in the business of overselling this right now. What we're shooting for, I don't want to play my machine learning method gives a better mean squared error than your machine learning method uniformly type argument. At the very least, we're trying to argue that it's comparable in mean squared error across a bunch of different settings. We did it across simulation settings, found the same results, but the problem with simulations is always they can be engineered so that you look bad or worse or something, good or bad or something like that. So that's the idea here. Then returning to our variable importance measure, and this is our focus. And as you'll see, this is coming along, and we're still working on cleaning this up. But across the 12 different seeds, we get a slightly different story than the other methods. where we only choose 21 of the variables in total out of the 50. So we're selecting from a smaller set of the variables, and a lot of the variables only come in 1 or 2 times. As before with the other methods with vote ideology, that's the one that seems to matter the most. Next is trust in parliament, which seems to always come in. And we seem to be picking up some of the same features, but to be completely frank, we just put this together this morning. And it's been honestly a bit fluid over the last few days. So I don't want to dwell on this particular figure. What I would like to say is our target would be to come up with a variable importance measure that can be analyzed and arguably give a better result in terms of how we interpret these things. Zenobia, was there anything you wanted to add on this figure?
No.
Okay. So when I say work in project, the reason there's only 12 different seeds instead of 100 is this is like, we're doing this now. So moving forwards, and here's where I'm opening up the door for advice or help with this. One of the things we want to figure out is like, we keep on doing better in mean squared error than random forests, and often better than generalized random forests, and like, you're not supposed to do that. So we're trying to figure out what it is and why. And we have some ideas, analytic and computational, but I could use some help in trying to figure out how to think through the problem, not necessarily answer it, but what dimensions we might want to explore. As well, we split half the data, and one of the things our boosting algorithm is missing is a stopping rule, but we're working on a GCV statistic that we think will do the trick. At the a GCV statistic, or more generally, a dimensionality measure for this. And we're playing with different ideas. Zenobia and I are back and forth on this. But once we get an idea of the dimensionality of the model, it becomes easier to construct a GCV or AIC or BIC statistic or something like that. One of the things we can get at that I think might be new is we can start to talk about the directionality of the effect, possibly. And this is something we're working on, but it's very easy because we're selecting 2 variables, as we can find interactions if they seem to be there in the data. We don't have to permute the x tildes one at a time. We can actually permute both of them for the pairs that come in. And then once we have this in place for mean squared error, it should be reasonably straightforward to code it up for deviances, hinge loss, the causal loss function for causal forests, those sorts of things. But we're trying to get mean squared error correct first. So in conclusion, I think that might have come out to about 20 minutes. Oh my God. So thank you all for your time.
That's okay.
Oh my God. You should see what happens when I have a paper. Anyways, thank you for your attention. I really appreciate it. And any feedback would be wildly appreciated.
Awesome. Thanks so much, Marc. I really appreciate it. So let's take some questions for the next 10 or 15 minutes or so. And you know, you can either just raise your hand, or you can either speak out, or actually, yeah, let's do hand raising in the gallery view. Yeah, Arthur.
So I have a question about GRF. So in Susan Ethy's paper, do they prove the following statement? As n goes to infinity, the probability of selecting noise variable goes to 0. Do they have this type of results in their paper?
I don't know if they have it for variable selection. I know they have consistency of the conditional mean under the concentration assumptions.
Oh, okay.
Which is the best, which is good. I don't know if they look at variable. I don't know if they look at variable selection or if that goes to 0.
Yeah,
so
because in Lasso literature, there are researchers providing the regularity conditions that Lasso can select a correct covariance with probability approaching 1 as n goes to infinity, right?
Yep, under some sort of sparsity or approximate sparsity condition, and the number of covariates of order law. You know all that.
Yes, yes.
But it's a bit easier in the regression setting because the variables are fixed in an important sense. You have to like enter them into a regression. Whereas here, there's massively more variables because you're considering each split.
Yes. And my second question, sorry.
Oh, and my understanding on the random forest side is that the random forest, the GRF, is designed for a fixed K setting.
Yes.
And there's been she has a paper by, I'm blanking on her name, but she's at Chicago and amazing. Oh gosh, I forgot her name, but she's in your stats department. He has a paper talking
Rina
about,
Barber, right?
what's that?
Rina Barber, right?
No, an Eastern European name.
Barber.
Was it, who's it?
Barber.
Barber?
Yes.
Okay.
Okay. Anyway.
Yeah, no. Anyways, I'm sorry for blanking on this, but
Okay.
yes, you're right. And she is putting the right concentration assumptions to allow K to grow,
Yes.
but I don't know how that ties into the implemented GRF package.
Okay. Thank you.
Okay, I appreciate the question though.
Yeah.
And I'll go back and take a look at that, but I do know the original Fogger and Athey papers focus on the fixed K setting.
Yes. Thank you.
Any other questions? Yeah, Robert, or do you prefer Robert or Bob? I think you're muted.
You can call me Bobby if you'd like. Some
All right.
Europeans can't handle it. I have a couple questions.
Please.
Some are simpler and some are a little bit just more conceptual. When you're describing the number of trees, is that for the is that varying both the eventual prediction of the outcome, or is that also included in the trees that are used to predict your X's?
Oh, the trees, yes. The trees used to predict our X's we keep as fixed at 1,000.
Okay.
There's some sensitivity to that variation. We're finding more tuning parameters in everything.
Yeah.
So when we do random forest and GRF, we actually fit it to 1 tree, 2 trees, 3 trees. I don't think we start at 1, but like we fit to 10 trees, 20, 30, all the way up to 500 or 1,000. And if you look at the mean squared error, you actually do get some variance in terms of number of trees fit. For us, number of trees fit, that corresponds to number of steps in the boosting algorithm.
Right.
But for the parceling out, we fit it at 1,000 because that seems to work. There is some sensitivity to that, but generally if it gets up high enough, we do fine. Okay, so that was my first question, just how to interpret the various pictures. My second question is about it's 2 additional questions. It seems like what you're estimating here is a little bit different than a marginal effect that we might be interested in, because in a random forest, the contributions do not have to be linear in any sense, right? And so when I think of a marginal effect, I'm thinking of a more linear relationship fundamentally, at least at the whatever the hyperplane is. And so I'm a little bit confused about how we should interpret this non-predicted X. And then my following question to that is, it would highly depend on all these other variables, nonlinear relationship of those to this. Yeah. So the analogy to linear regression is a little bit confusing because it's not exactly like the partialed out part of X anymore. It's a nonlinear function of it. Help me get through this. Because help me get through this answer. Because again, we're starting on this. In the regression, you can get the least squares estimate through partialing out the other X's, right? And we're trying to carry that intuition up to the random forest. So just as in a regression, a coefficient that you estimate can depend on the control set. Yeah. Right. And we're saying, so your point that the same thing happens here, we agree with. But my geometry interpretation of linear regression doesn't work. Okay. In this setting. That's my point. And my notions of marginal effects also don't work exactly the same way. And so my question is, conceptually, what are we estimating when we use this technology? So let me take a potentially dissatisfying stab at it while saying I appreciate the question. At this point, what we're working at, one way we can think about this is embedding the true conditional means in an L2P as a sufficiently high dimensional space. At which point we can get something, let me back that up a second. We're partitioning the variance in the outcome in a part that's attributable to only X and a part that's attributable to X to,
I'm
We're-
thinking of something like projection, right? So we're
Yeah.
projecting it into the space spanned by X. That's the
Mhm.
normal geometric interpretation for regression. And that's just not working in this context because
Is it?
it's not a projection. And so
But-
I don't know I'm not familiar enough with the higher dimensionality.
But it is still a
descriptions.
conditional expectation,
Yes.
right?
It's a conditional expectation, but the interpretation of it as a marginal effect is less obvious to me.
The Zenobia, did you have an idea on this? I very well might have to thank you and punt on this and think on it because we're still putting this together. So, but Zenobia, did you have a thought on this?
Not yet.
Not yet. Okay. So coming back to your answer, what we're trying to do, and if I could just head towards the theory that we're starting to actively work on, is we're going to embed this in linear spaces and develop some first order approximations to the loss function to answer that question so that it's locally linear at every point, and then show how it aggregates up. So we're going to take the loss function and do a first order Taylor expansion of it, which makes it linear at each point, and then partition that linear part into showing that, like, if you permute the X, in the way we're suggesting, it leaves one part of it unfixed and another part of it varies, and this is the part we're looking at. So we're ultimately going to expand this out into first order linear approximations, which is going to require us to be, our conditional mean to be in some sort of space of Lipschitz function, the class of Lipschitz functions, right? We need to be able to take these first order approximations and get the right answer from it. He'd be in the space with bounded first derivatives. So I think what we're going to do, to come back to your question, is at each data point, write out the answer as locally aligned, very, very close to the data, partition it in the way we're describing, and then aggregate it back up that way. Does that help with the question? Because that's sort of how I'm thinking of it, but we have to do that. Okay. Other questions on this? I really appreciate that, by the way.
Great question. All right. Well, if we don't have any other questions, let's move on to our second presenter. Since I'm the host, I feel kind of guilty presenting in the middle. And I want to make sure that everyone has a chance to present, especially if we go a little bit over time, in case you folks want to leave early. So we're going to kind of move on to the third presenter, or the third presenter on the original schedule. And so I'm just going to share my screen, and that would be Arthur and Robert, who have a very interesting paper. Unfortunately, I did not get the chance to read the full draft, but from what I read, they're doing something that seemed impossible before I started reading this paper, and so I'm really looking forward to you guys sharing this paper. So with that being said, Arthur, if you don't mind, could you hold on for like 1 minute while I take a quick break, and when I come back, would you you could start the presentation? Does that work?
Yes.
Okay, cool. All right. Hold on 1 sec. Thanks.
Yeah.
I'm going to let Arthur talk. So hello, everyone. We were talking about microphones earlier. This is my wife's podcasting microphone.
What's her podcast?
Called Linear Digressions.
Oh, that's awesome.
She did the machine learning course for Udacity when she was in grad school. And has been continuing doing a podcast spun off from it. Zenobia, what was the dependent variable of that paper?
It is the ideology. So the question we asked the respondents was, if there was a general election happening tomorrow, which party would you vote for? And then we coded the ideology of that party.
I see. Thank you.
All right, so I'm back. Arthur, whenever you're ready, you should be able to share your screen and start your presentation.
Let me share my screen now. So does it work right now?
Yes.
Okay, so okay, so this is Arthur. I'm a third-year PhD student from Chicago Political Science Department, and this is a joint work with Professor Gulotty. So he works on IPE and political methodology. So in this paper, we will talk about how to use instrumental variable to learn the ATEs of always takers and never takers. So IV estimation has been widely used in empirical political science studies to address the election problem in observational data. So if we allow flexible heterogeneous treatment effect, then IV only identifies late, which is an average treatment effect for complier group for compliers. So an implication of the heterogeneity assumption is that late doesn't equal to ATE, and also late doesn't equal to the ATEs of always takers and never takers. And so we believe that in the study of persuasion, researchers are interested in the ATEs of always takers and never takers. So in empirical study of persuasion, researchers are interested in the following parameter. So what is the effect of some information treatment on people's action of interest? So there will be two examples in this context. So first, in authoritarian government, the authoritarian authorities will use propaganda to persuade their people to believe in their performance. And in democratic societies, the democratic candidates will use campaign to persuade their voters to vote for them. And people may respond differently to this information treatment. For always takers, they may be the most responsive people to the treatment because of their high prior of the support of the state of the world. And for never takers, they may be the least responsive people to the treatment because they are low prior on the state of the world. Okay, so in this project, we will do four things. So to facilitate our extrapolation, so we first rephrase the IV model in Imbens and Anger's paper into the latent utility approach. And after that, we will provide a set of identification results, point and partial identification results on the ATEs of always takers and never takers. And we will provide simulation studies. However, I will not go through the simulation due to the time constraint. And finally, I will talk about applying our methods in Kern and Heimüller 2009 political analysis paper and do some extrapolation exercises. So first, so these are the four assumptions that you will encounter in any causal inference class when you are learning IV. So to use an IV to learn the to do causal inference, we need four assumptions: IV exogeneity, IV relevance, exclusion restriction. In addition, we also need monotonicity assumption. However, after Imbens and Angrist published this paper, there are so many critiques on the paper. So especially from Jim Heckman. So first, the first critique is that the monotonicity assumption is actually pretty ambiguous. To be precise, the IV monotonicity actually doesn't equal to the mathematical monotonicity. To illustrate my point, I will use this example. Okay, so consider we have an instrument where it takes three values, 0, 1, and 2. The mathematical monotonicity may imply one of this relation of potential treatment status. D0 smaller than D1 and smaller than D2. Of course, the order can also be reversed. That's mathematical monotonicity. But the IV monotonicity actually says for any Z and Z prime in the support of Z, either DZ smaller or equals than DZ prime or vice versa, almost surely. So this ordering actually fits the IV monotonicity assumption. So D0 smaller than D1 and D0 smaller than D2 and D2 smaller than D1. But this ordering it's definitely not that D is weakly increasing or decreasing in Z. So to conclude, so actually mathematical monotonicity implies IV monotonicity, but not the vice versa. And second criticism on the monotonicity assumption is that you don't have substantive interpretation of this assumption. So to be precise, what I mean is that there is no natural connection between the IV monotonicity and the rational choice theory. So conceptually speaking, what IV does in this context is that IV is shifting people's decisions of taking the treatment. However, you're restricting this, you're imposing this uniformity assumption in the sense that IV only shifts people's tendencies of taking treatment in y direction. That is, you either increase people's tendency of taking the treatment or decrease. So conceptually speaking, this is a little bit strange because in Imbens and Engrist framework, they allow very flexible heterogeneity in the treatment effect. But in the first stage, they are restricting how flexible IV can shift people's decisions into selecting the treatment. Actually, there is asymmetric relationship within this framework. So to provide a solution to these two critiques, Wittloso in 2002, he has a paper that tries to link the IV model to the selection equation in traditional literature. So now let's rephrase everything into the selection model. So it turns out that the monotonicity assumption, it can be reformulated as this selection equation. So this U is the latent utility that is all observable to the researchers, and the Z is the instrument, and V is some function that we need to estimate. But the intuition of this selection equation is that you are using instrument Z to shift people's valuation of taking the treatment. And people are having this utility threshold to compare the valuation of the selecting into the treatment versus not selecting into the treatment and making decision whether or not they select into the treatment. So by doing this, we have very nice interpretation of the first stage regression based on the rational choice theory. And because of this framework, this rephrasing monotonicity into this selection equation, the independence assumption, IV independence assumption, can be reformulated as instrument independent of the joint distribution of potential outcomes and the latent utility. So to repeat, as analysts, we don't observe latent utilities. Okay, and then for IV relevance, it's very, we only need the function Vz to be a non-trivial function of Z. That is, we can't allow Vz to equal to a constant. That's the pretty simple assumption. And then the exclusion restriction remains the same. And we also need a more technical assumption. That is, we need the latent utility to be continuously distributed. And it turns out that you can show these 5 conditions are exactly equivalent to the IV assumption in the Imbens and Engrist IV model. Okay, so because if we have this latent utility, we can now introduce this whole new treatment effect parameter called marginal treatment effect. So before we talk about this MTE, i.e. marginal treatment effect, let's do some normalization. So remember that we're assuming U to be continuously distributed. And this implies that we can renormalize the distribution of U to be a uniform distribution. And another implication of this normalization is that we can interpret VZ as propensity score. So when this event, when U, this random variable equals to little u, which is a realization of the U equals to VZ, when this event happens, this exactly describes the set of individuals who are at the margin of selecting into the treatment. Okay, because of this, we can define the marginal treatment effect as the average treatment effect for the individuals who are at the margin of selecting into the treatment. So this MTE framework is actually very, very powerful because many treatment effect parameters, say ATE, ATT, ATU, late, selection on the gains, can be rewritten as weighted average of MTEs. And these weights are identifiable. And so after we set up the framework, we can now talk about our extrapolation exercise. So remember that we're interested in these 2 target parameters, that is the ATE for always takers and never takers. And we also know that distribution of Y1 for always takers is identifiable, and the distribution of Y0 is identifiable for the never takers. But we still want to learn something about the ATEs for always takers and never takers. Okay. And remember, we also have this MTE framework. We will try to rewrite everything, these two target parameters, into weighted average of ATEs, weighted average of MTE function. It turns out we can. It's summarized in this theorem. So this theorem says that the ATE for always takers and never takers are just some weighted average of MTE function, and the weights are just some propensity scores. P0 is a probability of D equals to 1 when Z equals to 0, and P1 is the probability of D equals to 1 when Z equals to 1. So after we have this theorem, a natural question to ask will be, can we put strong enough assumption to help us point identify these two parameters? It turns out that we can. The intuition of this assumption that we impose is that, what if we impose parametric assumptions on this MTE function? That is, we either assume it's linear or parametric, and if the instrument creates enough variation on the treatment taking decision, we can point identify this function. And because we can point identify this function, we can point identify these two target parameters. Of course, because we know MTE and all these classic target parameters, say ATE, ATT, selection on the gains, we can identify. And this proposition summarizes the intuition that I just talked about. But of course, there are definitely criticisms on this proposition. So a natural criticism will be, why do we even believe in these strong parametric assumptions on a marginal treatment effect function? So people may not believe. And also, if you think about this assumption conceptually, it's actually very strange, because the motivation of MTE is that we want to allow very flexible heterogeneity of the treatment effect with respect to the unobserved latent utility. But when you are putting this parametric assumption, you're actually restricting the flexibility of such treatment effect heterogeneity. So to respond to this critiques, our approach, we ask ourselves, can we do partial identification? In terms of partial identification, what I mean is, can we identify a bound for the ATEs of always takers and never takers? It turns out that we can. And our strategy is to rephrase this extrapolation problem into a linear programming, or we can also call it linear optimization problem. Okay, so I'm gonna talk about the intuition about this linear program right now. So first, we need to remind ourselves that we observe estimates like OLS, late, and also these 4 sample moments where indicator function D equal to D, Z equal to Z times Y. These are the 4 sample moments that we observe from the data. And the nice thing about these estimates are that they are also weighted average of MTE function, and their weights are identifiable from the data. Remember, so these estimates, they're weighted average of MTE, and their weights are identifiable. And we also show that the ATE of always takers and never takers are weighted average of MTE. And these weights for always takers and never takers are some propensity scores, right? It's also, we can compute from the data. But what we don't know is the potential functional form of the MTE function. And these estimates, say OLS, IV, and these sample moments, they actually provide some information on the possible parametric space that the MTE function can take, right? And this same MTE function lie in this parametric space generates the ATEs of always takers and never taker. And an implication is that only a set of values for the ATEs of always takers and never takers will be consistent with the parametric space of the MTE function. And the parametric space of MTE function is given by this OLS, late, and sample moments. In other words, we can partially identify the ATEs of always takers and never takers. And of course, if our information is strong enough, the bound for the ATE of always takers and never takers can shrink to a scalar. And in that sense, we can still actually point identify these 2 target parameters. And this intuition is just summarized in this proposition. And so far, we have talked about rephrasing IV model into the latent utility framework and introduced the concept called marginal treatment effect. And we also show that ATEs of always takers and never takers are weighted average of MTE function. And we show that the parametric assumptions on MTE function guarantees point identification. But sometimes, if we don't believe in the parametric assumptions on the MTE function, we can do partial identification by doing this linear program. Okay, so now let's go to the empirical application. So we're looking at this Kern and Heimler 2009 Plateau analysis paper. In their paper, they're looking at the effect of watching Western Germans TV on Eastern Germans' support for communism. So they get the data, they get the survey data to do this research, and survey data the survey was conducted between 1988 to 1989, which is very close to the collapse of Soviet Union, actually. And of course, the identification challenge in this effect is that people are self-selecting into watching Western German TV or not, right? So to solve this selection problem, they use a binary instrument which measures whether people live in Dresden district or not. And this Dresden district is very far away from Western Europe. And because of its due to the topological reasons, people living in this district, they can't receive, it's very hard for them actually to receive the TV signal from Western German. And our conjecture in this context is that this self-selection may suggest that people may have some private knowledge on the potential treatment effect. And people are acting on this potential treatment effect to self-select whether or not you take the treatment or not, given the instrument, okay? So to remind ourselves, our target parameters are ATEs of always takers and never takers. So we first do point identification. So first we replicate the paper. So this is our replication. It's very close to the original results in the paper. In these regressions, we don't control for anything. The IV are super strong, by the way. And the results shows there is a positive effect of watching Western Germans TV on the support of communism for complier group. In other words, watching Western Germans TV actually increases people compliers' support for communism. To me, I think this is a very striking result. So now let's do some extrapolation, okay? So first, let's do point identification result. So again, we're parameterizing, where we're imposing linearity assumption on the MTE function, and we're getting those two extrapolated results. So the results shows that the effect of Western Germans TV is positive for always takers, and the effect of Western Germans TV on support of communism is negative for never takers. Although many people may disagree with us on these results because of the poor parametric assumption. But the more interesting results are from the bounds by linear program. So for the ATEs of always takers, the bounds are always pretty wide, but we think even we control the H cohort in our linear program. But I think this is driven by the small sample problem because there are only 2% of the people are always takers, which means there are like 30 something people in the sample are always takers. But the results for never takers, the bounds becomes very tight and narrow when we after we control the H cohort in our linear program. So the results shows that there is a negative effect of watching Western Germans TV on the support of communism for never takers. And our interpretation is that these never takers, given their high prior support of communism, they are acting as if they have private knowledge that they anticipate such negative effect of Western Germans TV. Thus, they self-select to not watch Western Germans TV. Okay, so to conclude, in this paper, we're trying to do some extrapolations on the ATEs of always takers and never takers using instrumental variable. So we first rephrase everything into the latent utility framework and define marginal treatment effect. And we also show that ATEs of always takers and never takers are weighted average of MTE functions. And we show that as long as we put enough parametric assumptions on this MTE function, the point identification is possible. But if we don't want to invoke this parametric assumption, we can also do linear programming, which is to rephrase everything into an optimization problem. And in the paper, we actually compare our linear programming approach, this partial identification approach, with many existing competing partial identification strategies. And it turns out our linear programming approach performs better. In terms of better, what I mean is you can construct narrower bounds with less assumptions, less additional assumptions on your data. Okay, and we also apply the methodology into this current Heimler paper. The interesting result shows that there is a negative effect of watching Western Germans TV on people's never takers' support for communism. And our interpretation is that these never takers, they're acting as if they are anticipating this negative effect of Western Germans TV. Thus, they self-select to not watch the Western Germans TV, given their high prior support of communism. And I think that's, and the final takeaway point is about whether or not this paper actually connects with machine learning. I talked with Bobby before. I think this paper is remotely related to machine learning because this is about optimization. And in Becker-Friedman Institute at UChicago, we have a conference called Optimization Conscious Econometrics, and we invite all the people from stats studying machine learning and optimization to talk about how optimization theory revolutionized the machine learning. So I think our paper actually still remotely relates to machine learning. Yeah, that's all of our presentation. Thank you. Yeah. Yeah. Yeah.
Sorry about that. I was double muted. Yeah, optimization is, thank you very much. That was excellent. Optimization is, what I was saying before was optimization is extremely important in machine learning. In fact, I took a class at Berkeley that was on only optimization. It was really fascinating, great class. And it was being taught by someone who was doing, was at Facebook AI research. So, you know, the knowledge of optimization and optimization problems is just, especially when it comes to these really complicated models like deep learning models where you have to, you know, they take a long time to train and they're extremely complex, and yeah, optimization is super important. So this is a great application of kind of optimization method. So anyway, I have a question, but I'm gonna kind of ask folks who are out there in other places if they'd like to ask a question to the presenter before I ask my question.
Arthur, you don't have to share your screen anymore. You can shut that off.
Yeah, you can just shut your share screen off.
Yeah, I think Zenobia has a question. Yeah.
Oh, Zenobia. Hey, sorry. Okay.
Oh, okay. I thought you yeah.
Anyone?
So,
yeah.
One question I had, because I shared Jason's concern that you're not supposed to do this, in the sense that I mean this in a good way, in the sense that identifying behavior and always never takers simply can't be done from the data.
Yeah.
In an IV.
Yes.
Right. So it literally, so like crazy things could be happening over there. And then you're using parametric assumptions to put bounds on those crazy things that are happening.
Actually, we're not. Our response is that we're not putting parametric assumptions, because it turns out this new latent utility framework is exactly equivalent to the IV model in Imbens and Angrist. So in that sense, in that linear programming extrapolation approach, it's completely assumption-free. Yeah.
Wait, it's assumption-free in what sense?
There's no additional assumptions.
There is no additional assumptions.
But you need a linearity assumption or something like that.
In terms of identification results,
yes.
In terms of formulating this linear program, we don't need any additional assumption, because all these treatment effect parameters, they are weighted average of some conditional expectation. So it forms a linear space. And conceptually, you can do linear programming. But to make the linear programming feasible, to make this feasible, we need to put some parametric assumption on the MTE function.
Yeah.
But that's why we loop so many parametric polynomial orders on the MT functions in our linear programming application. However, the bounds are actually not very sensitive to the polynomial order for never takers. Yeah, I think
So-
it's very robust. Yeah.
So one place to push on this in terms of presenting,
Yeah.
or in terms of the presentation, because the idea, at least in my head right now, is making sense.
Yeah.
It depends on that sort of linear extrapolation, right? And extrapolation problems are difficult because anything could be happening over there conceivably, right? So any information you're bringing in is by assumption.
Yes.
That said, some assumptions are better than others. So is there some way to build faith in your model in the observable data? So rather than check off 25 different models with different specifications and show you sort of get the same result, is there some way using the observed data or using some held out data or something like that to say, you know what, this data performs better for the compliers or something like that, and I have some faith it will extrapolate on outwards?
So now we haven't think about this because
Or what would a bad model look like
in our
in your
simulation,
setting?
yeah. In our setting, say for example, we have a proposition that if we put parametric assumption on the MT function, very strong, we say it's linear, and then we can point and identify everything with binary instrument, right? And in our simulation, we actually show if the MTE function is approximately linear, and then your extrapolated results will be very close. However, if the MTE function, the true MTE function, is not very linear, and the extrapolated results will be very far away. And that's where things can become very bad. But again, the linear programming approach is that since we're only approximating a unknown function within interval 0 to 1, actually in optimization theory, the Bernstein polynomial, if you use this Bernstein polynomial to approximate this, approximation will be very, very good. That's why it's actually very robust. Yeah, that's our response. Yeah.
Okay, so what's helping constrain the problem is you're only estimating a bounded function.
Yes.
So you could use some sort of, you said the Bernstein polynomials, or any sort of Fourier decomposition or something that just is any bounded basis function should perform well.
Yes.
Okay.
Furthermore, the bounds are constrained by the values of the observed parameters that are themselves weighted functions of the MT function. So it's actually using the fact that all of these regular observed things that are locally identified, like the late, like the IV estimate, like the OLS estimate, themselves put bounds on that space.
How does it put bounds on the space?
Because it's assuming that the MTE functions that we're trying to put constraints on have to hit certain values. In particular, we know the weighted values that they have to hit for those observed quantities.
For example, OLS and
Okay.
yes.
So it's not just a linear extrapolation. It's using the theoretical construct that there's this latent utility out there, and that's driving people's decisions to opt in or out of treatment.
So you can constrain the space of possible functions by enforcing that it
hits
give you the
values.
late back and gives you the least squares estimates back.
Yeah, and the conditional moments, the cross moment. There's some cross partials that we have to hit. So there's like 5 or 6 things that all have to happen all at once. And so then the additional question is actually not to really constrain the functions. It's more about a computational feasibility problem.
Yep. So then you do have to be assuming that the the MTE function doesn't change by compliance status, right?
No. The MTE function it's the function for across all the individuals. Yes.
Okay.
Yeah.
So it has to be smooth though.
It has to be smooth.
Yeah.
But so what's precluding it from being just really crazy for never takers and you not knowing that?
Then
it wouldn't. Which part of it?
I'm sorry. I'm. You need to be assuming that there's some similar function running from the compliers that are observed to the always takers and never takers, or at least some similar function class or some space of functions, right?
Some space of functions, yes.
Okay, and then you're limiting the space of functions on the observed data and assuming that carries through to the always takers, never takers.
Yes, because the same selection equation drives the decisions for every people in the data, complier, always taker and never taker. That's the intuition. Yes.
Okay.
That's why this approach is actually choice theoretic based.
Yes.
Yes.
And I like the Heckman, how do you say the name? Vitilisil?
Vitilisil.
Vitilisil. I like that better than the Angrist-Imbens approach. It just takes a lot more to get there.
Yeah, Vitilisil is a Heckman student, by the way.
Is it? Okay.
Yeah, he's at Yale right now. Yes.
Because their works on that has been interesting. Okay, cool. I think I almost buy it, but I'll send you an email after I look at the paper more closely.
Yeah, yeah. Thank you. Thank you. We appreciate that. Yeah.
All right.
Yeah.
Any other questions?
Can I add a quick suggestion?
Yeah.
So you mentioned in your presentation that the exclusion restriction assumptions still have to be met when we use your method to estimate the MTE. And I was just thinking, when you talk about your example in Dresden, is exclusion restriction really met here? Like, because when you explained the never takers, it seems like they by choice don't choose not to watch the West German TV. And I was thinking, then is it possible that people choose to live in Dresden to begin with because of their existing like pre-existing belief? If that's the case, then it doesn't seem to me that like so it's not exactly related to your project, but I feel like the exclusion restriction assumption here is a little bit shaky.
So can I respond?
Yes.
Okay. So actually in Kern and Heimler paper, they justify this. Before the collapse of Soviet Union, the labor market is very, very ill functioned. So spatial sorting is actually impossible. That's how so people you actually can't move freely in Eastern German. Of course, I'm not an expert on Eastern German, but that's what their papers say when they are trying to justify the exclusion restriction. Yeah. Does that answer your question or no?
Yes, I will write you an email later.
Yeah. Thank you. Yeah. Thank you.
All right. So so I just had a question that was a little bit more general, and that is, you know, the kind of conceptual idea of estimating the treatment effects for always and never takers.
Yeah.
So one thing that I don't and perhaps you can help me out with is what, like, is there like a subset of problems in which this estimate in which the very idea of estimating treatment effects for always or never takers breaks down? Because I was just kind of trying to think through different types of examples where you would have situations where you have compliers, always takers, never takers, but in one situation, let's say like a vaccine or something, because that's what's on everyone's mind, right? It's clear that there's effects, there's treatment, there's like if the vaccination is the treatment and the disease probability of disease or whatever it might be is the outcome. Yeah. Then it's clear that there would be effects for always and never takers because of the compliers, right? Like, in other words, the compliers taking, like, let's assume like there's like there's a contained population. There's a lot of assumptions I'm building in there. There's like a contained population and everyone is randomly assigned a vaccine, something like that, right? Yeah. So then the compliers would have effects on the always and never takers in terms of their probability of disease. But well, let me just finish. But like, so that's one context where I think that makes a lot of sense. But then, like, if you take, like, let's say the treatment is a heart pressure medication, I'm getting very practical, like a little bit away from political science. Like, what would that mean conceptually to estimate the effect on blood pressure of always and never takers, since the compliers don't have any kind of, or they shouldn't have any influence on those two other groups? I don't know if that makes complete sense, but I'm just trying to work through, it's a very interesting paper, and it kind of introduces an idea that is conceptually very interesting and a little bit hard for me to wrap my head around. But I was wondering what your thoughts were on that.
Can I respond?
Yes.
Okay, so for your first question, if I understand correctly, you're asking potential spillover effect, right? So the
Kind of.
Yeah, so actually in this framework, we don't allow spillover effect. The suitable assumption is still there. That's an
Okay.
implicit assumption. Yeah. And to your second question, the blood pressure example. So remember that the main motivation in this approach is to say we need to link our instrument on the treatment, on how we need to link how instrument affects people's treatment taking decision based on
Okay.
social scientific theory. So I think if you don't have good theory on justifying that, and then we probably wouldn't suggest you to do this framework. Yeah.
Interesting.
What I would say is you should think of as the prototypical example for this as an encouragement design.
Yeah.
Where
okay.
we don't have control over whether you get the treatment or not, but rather we can encourage you to take it, just as the government can't force you to listen to its propaganda, but it can encourage you to listen.
I see.
And we can study things on the encouragement, but then there are people who won't take it up even if you encourage them, and there are people who will take it up despite the fact that they were never encouraged. And those non-compliers have potential treatment effects in a study in which they were forced to take the treatment. And that forced to take the treatment is like interesting for social scientific context where you're thinking about expanding the program beyond the people who are just marginally encouraged. So like in the case of the vaccine, let's suppose that we wanted to figure out the effect of a vaccine, but it wasn't something it was people were signing, it was something people going out and buying in a store. And the government couldn't control, didn't want to invest in a real experiment. So what they did was they said, let's compare the stores that are open more often and less often. That kind of encourages people to go buy this thing. Well, some people are going to get the vaccine even if the store is only open for 5 minutes, and some people will never get the vaccine even if it was open for another 5 minutes. And so those non-compliers are maybe the most vulnerable people in the population that you want to know, or the least vulnerable people in the population that you want to know the effect of this drug is. And so this technology is designed to target those two populations, the people outside the people who are most encouraged by the instrument.
I see.
And it's not so much about the general equilibrium effects that you're describing, which are also very important and something you could get at with a model, but we're not there yet.
Yeah,
very interesting. Yeah, no, that's very helpful. And if that's the case, I don't know how far along you are on this paper, but another example that you might want to consider, just maybe thinking about, or at least thinking about a response to, if someone else mentions it, is the kind of Vietnam lottery. I think that sounds like it might be a good example for this particular design, and it makes it clear that you're conceptually what you're interested in is kind of like this subset of problems where there are instruments which encourage behavior, encourage people to take the treatment, right? Because I mean, a lotto is technically the Vietnam War lotto is random, but you also, again, the local average treatment effect is also for the compliers. Like you have to not only get the lotto number, the right lotto number, you also have to, some people went to jail, they didn't care, right? So you also have to be willing to go be deployed. So yeah, so just something to consider. This is very interesting though.
Thank you.
Yeah, well, thanks for the paper. It's great. Okay, so I guess that then I am the only person left for this panel. And we're a little bit over time, so I'll try to make my presentation quick. And if you guys have questions about things I might have skipped, I'm going to I'll just fill in the gaps with the answers to those questions. So let's I'm going to share my screen now and start talking. All right. So I already kind of. Can everyone see this? Okay, great. All right. So I'm going to put this full screen. All right. So thanks everyone for coming and participating in this panel. I really appreciate it. My name is Jason Anastasopoulos, and I'm an assistant professor at the University of Georgia. And I study like kind of machine learning and causal inference and other topics in political methodology like text analysis and image analysis and deep learning to a lesser extent. and I also do work in bureaucracy. This is a paper that I'd really like your feedback on, and it's something that I've been thinking about for a while. So thanks for taking the time to watch this presentation. Okay, so I'd like to give you a little bit of a motivating example as to how this work had started. This is what I looked like in 2013 when I was a grad student. I was kind of like clean shaven and, you know, probably about 40 pounds lighter or so. And, you know, that was before I started this paper that eventually got published in Electoral Studies in 2016 called Estimating the Gender Penalty in House of Representative Elections using a regression discontinuity design. And in this paper, this is actually part of my thesis. And in this paper, I used an RDD where the primary vote share was the forcing variable and the outcome was whether a man or a woman was placed on a ballot for the general congressional elections. And what I found through doing this study was that there were basically no effects. So there was no gender penalty per se for being a female candidate or having a female name on an election ballot in the general election. Now, this paper actually ended up taking 3 years to do, and by the time I finished with the publication process, you know, I kind of looked like someone who had been sitting in a cabin for many years with a long beard, and you know, in part that was due to the stress that was required for publishing this paper. And but I learned a lot from the process of publishing this paper. And I learned a lot about RDDs, and I learned a lot about the publication process. And so the motivation for this current paper comes out of what I learned about from what I learned about RDDs. And the one thing that I learned was that RDDs have many researcher degrees of freedom, probably more so than almost, you know, than a lot of other types of causal inference models with observational data. Now, the comparison I'm presenting here is one in which I'm just comparing on the left-hand side. This is the case where if you just estimated a treatment effect and an average treatment effect using a regression model with a randomized treatment, right? And so your kind of researcher degrees of freedom there, the things you have to consider is, well, what's your dependent variable? Okay, what's your treatment? That's the obvious kind of thing that you have to figure out when you're talking about research design. And you know, if you decide to, you can also consider throwing in pre-treatment covariates. And there's some evidence that including pre-treatment covariates will improve the efficiency of your treatment effect estimates. But when it comes to regression discontinuity designs, you have those three elements, but you have a lot more, right? And I'm going to say that there's about a minimum of 9 knobs that you can turn and you could kind of play with in RDDs. And then so in addition to those three, right, dependent variable treatment, pre-treatment covariates, then you have the forcing variable, okay? So, you know, those are kind of fixed things, right? So those 4 are just the basic elements of RDDs. But then you have, well, like what kind of kernel are you going to use, right? And you have several kernel choices. What bandwidth will you use? Will you use an optimal bandwidth, or will you use a fixed bandwidth that's based on some substantive concerns? What method will you use to choose the bandwidth? There's the IMBIN's, the IK method for bandwidth selection, and you know, I believe there's other methods that have been coming out recently as well. Will you subset your data before you estimate the treatment effect? You know, what type of model will you estimate? Will you have a, you know, second degree polynomial, third degree, you know, and so on and so forth. So there's many researcher degrees of freedom when it comes to regression discontinuity designs. And so one of the problems with this is that, you know, as researcher degrees of freedom increases, you'll tend to have more false positive results, right? Okay. So this is, hold on one second, guys. Okay. Classic working at home moment. My son just came to the door. Okay, so so researcher degrees of freedom. Yeah, so you have a lot of them with RDDs, right? And you know what psychologists know very well doing experimental studies is that the more kind of knobs and dials you have to tweak in your experiments, the higher the likelihood of getting false positive findings. And I think that makes sense, right? And in addition to that, right, you also have treatment effects that tend to be, you know, I'm going to call them underpowered, but I'm going to, you know, that might be a little bit unfair. Another possibility is to say that they're low N, right? So, you know, if this is just a brief list of very like high impact important studies in the literature, and I took the lowest number of observations that the authors had estimated a treatment effect for, and you could see that, you know, there's some studies where there's like 15 observations that people use to estimate the treatment effect. In some studies, there's like, you know, 35, and some in the higher N ones, there's like 165 and so on. But you know, there seems to be this problem of, especially when the kind of optimal bandwidth is finally selected, of having a relatively low number of observations. And I think it's been confirmed by other folks that I've spoken with who have you know, done estimated RDDs. And I actually had that problem in my paper as well. When it was time to choose the optimal bandwidth, and I had used the IK bandwidth, my degrees of freedom were pretty small, right? Okay, and so we have this high degree of researcher degrees. We have a lot of researcher degrees of freedom. We have relatively underpowered or low N, you know, studies where these treatment effects are estimated. This kind of environment where the treatment effects are estimated in, and in addition to that, we have many different types of pretreatment covariates that people like to throw in their model. Now, this is again the same list of these studies. And so, you know, in some studies, people will throw in just only fixed effects. So, you know, in the Zacconi study, which I'm going to talk about, the author throws in year fixed effects, region fixed effects, sector fixed effects in this Russian firm data, but he also throws in time varying covariates. And in some other studies, the authors just put in some, you know, time varying covariates. And, you know, there's really no clear kind of, you know, rule or anything of the sort when it comes to adding covariates to, you know, for adjusting treatment effects in RDDs, right? And so now the problem with all of this is that the practice then of including pretreatment covariates then creates a situation in which treatment effects tend to be unstable, right? So in the small, and you know, I think everyone, that's kind of intuitive to everyone. Everyone would understand that this is the case. But let me give you a little example. This is just from you know, this simulation is actually not in the paper, but you know, you can see how sensitive treatment effects are to the inclusion of covariates using this example. And I'll show you more examples with real data next, and also a little bit later on. So in here, you know, I simulated with 100 observations you know, an election forcing variable, a close election forcing variable, F, which is, you know, is a random uniform distribution between should be negative 0.5 and 0.5. And I just also constructed two random, you know, randomly generated covariates that were weakly correlated at, you know, R equals 0.2. And I included them in the model, okay? So let's take a look at the treatment effect. This is this tau right here. That's the thing I want to point your attention to. And this is also using the kind of Colonico, Cattaneo, and Titiunic robust measure, right? So I included that as well. So the treatment effect estimate with no covariates was 0.036. And the treatment effect with two covariates, with these two randomly generated covariates that have a moderate correlation, was 0.09. That's a very large difference, right? And we also see, of course, that the bandwidth estimated is different, and so on, right? So there's, you can see that the treatment effect itself can change quite a bit when you include covariates. But if you don't believe simulations, which I don't blame you for doing, because I don't believe a lot of them either, let's take a look at at some real data. This is from the Zacconi paper that I'm going to talk about, which I used as the example for this particular paper. And you could see that so to give you a little bit of some brief background about what this paper is about, the outcome variable is, firm profitability, and the regression discontinuity, the treatment that Zacconi is trying to estimate is whether, a Russian CEO who wins an election, how that affects their firm's profitability. So the Russian CEO getting elected is the treatment, and then the forcing variable is the close election vote share. So the treatment effect here is basically, I forget what the exact units are, but it's some kind of, the outcome is firm profitability. So if you see this in his original paper, this treatment effect, this 0.146, this suggests that, a politician who was barely elected to office, their firm increased in profitability by, let's say, 14%, right? And so that's his treatment effect, which includes, all these covariates that I had mentioned before. But what if we kind of trim some of the covariates in a certain way? And this is the method that I'm talking about, this adaptive lasso method, which basically only trimmed 4 covariates from the original model. We see that the treatment effect changes significantly to 0.102. And we also see that even though the standard error actually decreases quite a bit, the statistical significance, because the treatment effect point estimate dropped, that actually goes down quite a bit. That p-value increases quite a bit. Okay, so you can see that there are pretty big differences that can be that including or excluding covariates can make when we're estimating these RDDs. But should we get rid of covariates altogether? Well, I don't think necessarily we should do that, or we have to do that. There's a lot of theoretical research that's been done by CCT, and they found that the inclusion of covariates does tend to improve the efficiency of treatment effect estimates. So, well, if that's the case, then what kind of solution do we have? I mean, if we say we want to include covariates to improve the precision of treatment effects on the one hand, but on the other hand, we want to kind of prevent the situation where people might be gaming the system, or treatment effects might change too drastically when we estimate them in these kind of relatively small n contexts. So what do? And I think the solution that I provide in this paper is that if you do want to include covariates in your regression discontinuity design, you should include them in a way that allows for a kind of an automated model selection procedure to remove them or to exclude them according to some kind of optimization criteria, right? And that optimization criteria is basically minimizing the mean squared error of the of this model that you're estimating, right? And I got the inspiration for this from some literature in the kind of experimental context, which actually dealt more with high dimensional problems. And so one of the first papers that came out, to the best of my knowledge, although there might be other ones that came out before that, was Blonariz. I'm not sure if I'm pronouncing the name correctly, et al. And that was a paper on lasso adjustments of treatment effect estimation in randomized experiments. And so what the authors in that was actually a PNAS paper. And what the authors of that paper found is that they kind of developed a whole means of selecting covariates to estimate treatment effects in randomized experiments where there were a lot of covariates available and people really didn't know what covariates they should include or exclude. And Wager et al., I think I'm pronouncing his name correctly. There's in the same year, and in PNAS as well, he also kind of did a paper on high dimensional regression adjustments in randomized experiments, where basically the idea was, well, how can we optimally adjust treatment effects through the inclusion of covariates using these automated variable selection methods like the lasso. Okay, so at the end of the day, what these folks argue is that the best way to adjust treatment effects in randomized experiments when you have like a kind of a lot of covariates, these high dimensional contexts is.
Hey, Jason.
Yes.
I'm having a computer issue. I'm gonna have to restart my computer. I'll be back on in like 2 minutes.
Oh, okay. Okay.
Okay.
Yeah. So let's. I'm just going to keep continuing in the interest of time, but so what they argued was the way that you should apply the lasso is to basically estimate your model and then use the lasso as a variable selection procedure. Obviously, you're not going to use the treatment effect estimate from the lasso itself, right? Because that's going to be biased. So you just estimate them. You estimate the whole model. You apply, the lasso penalty, and then the lasso basically tells you what variables to shrink, and then you re-estimate OLS and get your final treatment effect. And they have some theoretical results which show that this is a pretty reasonably stable method of minimizing or increasing precision and kind of minimizing the variance of the overall model. And of course, like one thing to consider is that you want to minimizing the variance of your model, right? The kind of sigma, the overall MSE, does have effects on your the standard error of your coefficient estimates, right? So it will increase the precision of your treatment effect estimate, right? Okay, so my solution in this paper is not that creative because it kind of builds upon these other works, and the solution is basically well, what if we applied the same kind of automated variable selection procedure, but to regression discontinuity designs, right? What if we just applied the lasso to RDDs when we estimate treatment effects? What would it give us? And the argument that I make in this paper is that it can actually give us, especially in these contexts in which hold on a second, let me let Marc in. Sorry. So especially in these contexts where, let's go back here. Especially in these contexts where we have a small number of observations, as I'll show in simulations later on, we can really get the benefits of including covariates while minimizing the costs. And so I developed a procedure for incorporating the lasso into treatment effect estimation for RDDs. And that's what I call the principled estimation method of regression discontinuity designs. And it's basically a four-step process that's based on the other papers which had adjusted treatment effects using the lasso, excuse me, using the lasso in this randomized experiment contexts. So in the first step, the researcher selects some pre-treatment covariates that they want to include. And these should be based on substantive concerns and can vary from model to model. Usually these might be something like fixed effects or other things like that. And if it's a closed selection variable, it might be changing demographics and things like that. In the second step, we have adaptive, what I call adaptive lasso regularization, and that's the kind of innovation that I argue is the thing that I'm kind of bringing to the table here. And so basically from the model from step one is passed through this, what's called an adaptive lasso. I'll explain what that is in a minute. And some covariates are selected out, right? After those covariates are selected out, then we move to step three, and the kind of final model is estimated, right? Now, the covariate adjustment part here in between steps 2 and 3 is such that I keep all of the kind of core elements of the regression discontinuity design the same. So there's the forcing in the local linear regression, the forcing variable is not penalized. Obviously the treatment effect is not penalized. The only thing, if there's the interaction, if we use the difference method, the interaction between the forcing variable and the treatment is not penalized. The only thing I penalized is any additional covariates defined by the researcher, right? And so then in the final estimation, the model selects out the covariates that should be removed. And finally, we do a kind of CCT robust estimation and get our covariate adjusted treatment effect at the end. So I'm going to try to go through these relatively quickly in the interest of time and explain each of these. Okay. And then I'd like to go over an applied example by Zacconi and some simulation results. And I'm going to try to breeze through a lot of these quickly. The important part is I just wanted you guys to get this the general sense of what the algorithm is here. Okay, so I think everyone pretty much knows what estimating a treatment effect for RDDs entails. So I'm gonna skip this. In this paper, I basically used the local linear regression method, and the focus of this paper is pretty much on tau hat, right, and covariate adjustment of tau hat. So the covariates are this big X beta matrix, and all of the selection that the adaptive lasso is involved in is on this X beta matrix, right? The covariates that we have here. Okay, so yeah, researcher pretreatment covariate selection. I'm just gonna kind of skip that and move on to step 2. So let's talk about the lasso regularization. So in the initial model, you're just estimating a local linear regression, and what the model is selecting out, the adaptive lasso model is selecting out, is the subset XS of the entire covariate space, right? And so you might wonder, like, well, what is the adaptive lasso, and why would you want to use it here? Well, I'm going to talk about that in a second, right? So this adaptive lasso is basically doing the covariate selection for the final model that you're estimating with the CCT robust estimation. All right, so for those of you who aren't familiar, although most of you might be, since this is a machine learning and causal inference panel, ordinary lasso regularization involves just estimating this kind of loss function, but with a penalty term included here, where each additional variable is penalized, and there's a kind of tuning parameter lambda, which is estimated using cross-validation. The adaptive lasso is a kind of a slight variation of the original lasso, and the reason I applied it in this case is because, at least according to its originator, Zhu, is that the adaptive lasso has oracle properties, and it thus tends to select out models in a way that are correct according to at least some standards. So let me talk about, I think one thing I skipped was why the ordinary lasso might be a problem in the first place. One of the problems that the ordinary lasso has is not that it doesn't do a great job of minimizing the mean squared error of a model. It does a great job doing that, but it tends to minimize the mean squared error of these linear models in a way that is somewhat random, right? So if there's a true model that you have out there that you know is the correct model, right? Lasso will not retrieve that correct model a very high proportion of the times, right? Whereas the adaptive lasso, for the adaptive lasso, that tends to be less the case, right? It has these oracle properties which allow it not only to minimize the mean squared error of the model through covariate selection, but also to select the quote unquote correct model, right? When simulations were done on the basis of some ideal model that was proposed originally. And this kind of makes it a very stable lasso method for selecting covariates in cases where, again, you don't want the treatment effect to change drastically when you select covariates, when you're kind of selecting covariates out, right? And it also, because it involves just the placement of a weight parameter in the lasso penalty, it's easy for you to incorporate some zeroed out weights for RDDs. But really, it's really the oracle property that kind of made me think about the adaptive lasso as opposed to the regular one for this context. And I could talk about about the adaptive lasso a little bit later if you'd like, but this is basically, so like here's the original lasso, that's the penalty, right? The L1 penalty. And the adaptive lasso also has an L1 penalty, but now we have this kind of omega weight. And the omega weight is just basically 1 over the absolute value of the parameter to some power, right? And this parameter, this is another kind of tuning parameter that's estimated via cross validation, the gamma. Okay, so you apply, so we're on step 3, right? So you apply this adaptive lasso method, and I kind of developed a whole R package to implement this. And some covariates are shrunk and some are not. Again, the way it's designed is so that none of the quote unquote main effects of the model are shrunk. Those are all kind of, they're not penalized at all. And the final model is the kind of modified, covariate set. I call this X naught here. And so, then you have some options as to what, how you want to choose bandwidth, right? So once you've selected those covariates out, you can either estimate your final treatment effect using an optimal bandwidth, which is what most people will tend to do, or using a fixed bandwidth, which tends to be done in the small, in the kind of not the small NRDDs, but the close election RDDs, where people sometimes the optimal bandwidth will be way too far away from the cut point, like 10% or something. So there's, if I remember correctly, there was a kind of rule that was published that you should estimate at least, you should at least estimate some kind of 5% window around the cut point when you have these close election RDDs. And I'm trying to remember exactly where that paper came from, but I see this rule being applied in many of the papers that I've seen while doing this research. Okay, and then finally, it's just, everything is just normal after the covariates are selected out, and you just do CCT robust estimation, right? Where you're basically just estimating the treatment effect with the covariates that had been selected out by the adaptive lasso model. All right, so let's just go through quickly an applied example where the adaptive lasso was, or this principled method was applied in through a replication of a paper published in the American Political Science Review by Zacconi in 2018. So Zacconi, his paper is part of a very interesting literature which uses close election RDDs to explore what the returns to office are in Russian firms, right? And so, or I'm sorry, in Russian government. So as I mentioned before, his outcome is firm profitability of a group of firms, and in Russia, and his treatment is whether the kind of board members of those firms were elected to office or not, and the forcing variable is basically vote share for these elections. And so what he finds, and this is not my plot, this is actually taken from Zacconi, is that there tends to be a relatively large increase, at least at this, when we look at the local average treatment effect here around this margin of victory in firm profitability as a result of being elected to office. Now, an interesting thing that someone else had pointed out when I presented this last time was, why does profitability drop so much when these individuals barely lose the election? And I don't really have a good explanation as to why that is. You'd have to ask the author. What's that?
They were hoping to win.
Yeah, apparently. Exactly. Maybe they spend too much money on their on the campaign or something. That could be too much of their company's money.
Or their opponents won the election and then crushes them.
Oh, then crush them. Yeah, there you go. Man, that's a great point, actually. Okay, so here's the Zacconi estimates a couple of models in this paper, but here's the general form of the models that he estimates. I mean, when I say a couple of models, I mean he uses one or two different dependent variables, but the general form is as follows, right? he's most concerned with this district win. So that's his treatment effect of being elected for these officials. And then he has, he uses kind of typical, diff and diff local linear regression with the vote margin and the interaction between the district win and the vote margin as like, you can call this like your main effects or whatever. And then the covariates he includes are a group of fixed effects. Those are represented by Y, S, and R here, and some time varying like candidate and district demographics, right? And I forget exactly what the districts were. They were I don't know that much about Russian geography, but there were several levels of geography that were included as controls in this model. All right, so let's take a look at the treatment effects and how they change when this procedure is applied. Now remember, I didn't do anything to this, okay, except for literally just use a lasso method to select out covariates, right? That's all I did, okay? In the original, this is one regression that was done, is we have the treatment effect was 0.146, is what I had talked about before. And when 4 covariates are removed, which were shrunk to 0 by the adaptive lasso methodology, this kind of our treatment effects shrinks to 0.102, and the standard error also decreases. Okay, so this is these two results. The first two are where the IK bandwidth was used to estimate the treatment effect. He also does another set of analyses where he chooses a fixed bandwidth. That's the 5% bandwidth, and those are the other 2 columns, the original 5% APSR and the adaptive 5% models, right? So this is where like we instead of using the IK bandwidth, I forget. So the bandwidth here you can see is pretty like high. Okay, it's 11%. That's a pretty big bandwidth in this case, right? So that's why he chooses this 5% bandwidth to just check the robustness of his results. And in the 5% bandwidth case, his treatment effect increases. So originally it's 0.146, and after that it's 0.198. And I still find that the effects are statistically significant after applying the adaptive lasso procedure. But there's a huge, like the procedure only removed 2 covariates, 2, right? And there's a significant number of observations. It's not like it's tiny, it's 201 observations. And through only the removal of those 2 covariates, we see a drastic decrease in the size of the treatment effect. Yeah.
What were the 2 variables?
That's a good question. I should actually find that out. I think I had meant to figure that out, but it just kind of slipped my mind. But I will try to figure that out because I'm very curious to know what they are as well. Okay. So, all right. So let's. Okay, so that's the applied example. Again, you can see that there are some nice things that come out of using the lasso to select out covariates. We do get it is clear that we do get these kind of smaller standard errors at the very least, right? Okay, so let's talk about some simulation results. Now, of course, if you're going to apply a method like this, you want it to improve the precision of the treatment effect, and it should theoretically, but when it comes to small in context, there's a lot of randomness that might occur, and that's why I wanted to demonstrate that this method would actually work using simulations. And also the adaptive lasso it's kind of a method that has not been used that frequently in the literature, to the best of my knowledge, even since its publication and since the publication of that original paper in 2006 by Zhu. So I did a series of what I call realistic simulations, and I'm happy to talk about them after the talk, but basically these simulations had were based on real parameter estimates. So imagine, taking real means and variances from a real data set. I actually took it from Zacconi's data set, and then generating simulated data sets on the basis of those parameters alone, assuming that each variable comes from a standard normal distribution. Right. Well, each one that should come from a standard normal distribution. Some come from a uniform distribution. The way that these simulations worked is that, this is the true model, right? That should be captured. And so the outcome variable, right? The simulated, this would be like a simulated firm profitability variable, YS, is equal to 0.3 times the simulated district win. So 0.3 is the is the true treatment effect, and all we have here is like the typical diff and diff model. So there's like no covariates. In other words, covariates should not be included in this model, okay, in the true model. And I compare. So this is the true model, right? And the true treatment effect is 0.3. And then, but the estimated model is the same kind of true model here, but with some covariates that are included, that are based on using some realistic assumptions about what those covariates should look like. And I do these, so this first set of simulations is based on an n equals 500 sample, and I do 2,000 of those simulations. And so let's kind of see what that looks like. So there's the two performance measures that I look at are percent coverage and bias, right? Of the treatment effect. So how far away on average for each simulation is the estimated model away from the the true model. And so this is the distribution of the simulated treatment effects for the adaptive lasso model. That's this model with this peak here in gold versus the conventional. And as you can see, the estimates are, because the adaptive lasso model basically selects out those extraneous covariates. These estimates kind of bunch more closely towards 0.3, the true treatment effect, than when we include the covariates without any selection. Okay, and let's look at some of the other numbers, and just these are just averages. And I kind of explore this using both a variable bandwidth approach and the fixed bandwidth approach. And you can see that when there's variable bandwidth, so basically we just let the IKA procedure select the optimal bandwidth, we find that the adaptive lasso, the bias is 0.27, and under the conventional method, the bias is 0.397. So that's a statistically significant difference there, right? When we let the kind of IK algorithm choose a bandwidth. Percent coverage, I think the results are much more dramatic, not surprisingly, because the point is to improve precision, right? So percent coverage is about 95%, which is what we would expect for the adaptive method. And for the conventional method, when we include these extraneous covariates, it is 70%. And that difference is also statistically significant. Okay, what about when we fix the bandwidth? So when I say fixed bandwidth, I mean like constrain it to 5%, and we do the same, we do the same simulations. Well, in that case, when at least for this simulation in particular, when the bandwidth is fixed, there's not really too much difference in terms of bias. So the adaptive method and the conventional method returns the same, roughly the same average bias. However, once again, in terms of coverage, which is, again, that's the whole point of this, is to improve the precision of the treatment effect estimate. So it makes sense in many ways that coverage will be better. In terms of percent coverage, we see that adaptive recovers the roughly what we would expect for the percent coverage, and conventional does significantly worse. Okay, so now that's with us, n equals 5. This is like a set of simulations set to n equals 500. What if we do some simulations where we vary the number of observations under this using the same models, and look at percent coverage and bias for lower n RDDs to higher n, or to asymptotically higher n RDDs? What do we get there? So each of these points here, so on the x-axis here, This is the number of observations. And for each observation, I think the observations were done in batches of 5, right? So there was 80 observations, and then there were 1,000 simulations done with 80 observations, 1,000 done with 85, 1,000 done with 90, 95, and so on. And the average percent coverage for each N is basically documented here. And so you can see that the coverage, when the number of observations is relatively low, a percent coverage for the kind of standard method when we include these additional covariates is much, much worse. And it does get better as the number of observations increases, and they almost kind of converge as we go to 400 and so on. But you can see that the adaptive method still tends to do better and is significantly more stable across all low end to high, from like 80 to 400 observations. And we see a similar pattern with bias, but with bias, this is basically average bias again over these simulations for each N. The average bias is lower for the adaptive method when we apply the adaptive method in the lower N context, but they both kind of converge to roughly the same value, roughly the same value as we go past, say, 200 observations or so. You can see this in the line. They basically kind of become the same. Okay, so conclusions. I think including covariates is good, and in the case of RDDs, and it's a practice that should be done. There are certainly theoretical results to back that up, but it can be problematic for low-powered or underpowered designs. And this method provides a way to, include covariates in a way that is that allows the kind of treatment effect to remain relatively stable, and to retrieve a kind of optimal treatment effect, or at least to basically achieve an optimal or estimate an optimal treatment effect that is, has the highest precision possible, which is pretty much what you want to do when you include covariates anyway, right? So the way I like to frame it is that this is a kind of method which kind of minimizes some of the drawbacks at the end of the day of including covariates for the types of models, the types of RDDs that we estimate, while maximizing the benefits. So that's it for me, and I look forward to your questions. Yeah, Robert.
Well, thank you for the presentation. I like how you're really thinking about the applied researcher when you're setting up your presentation. And the one thing I was wondering about is the selection of the selection stage when you're doing the adaptive lasso does not include the treatment when you're doing that that exclusion of certain variables. And I was wondering what the consequences of that would be for subsequent analysis. So if we're thinking certain variables matter a great deal for the relationship between the treatment and the outcome, which is presumably why we're including the covariates, what happens when we're not including the covariate in the selection part? We're just picking things that predict Y really well, conditional on relative to other covariates, but not our treatment.
So the treatment and the forcing variable, those are included in the adaptive lasso model. They're just not penalized.
No, I mean, but in the from what I understood, when you're doing the first stage, when you're selecting the variables that will be included or not included, it's all done in one process. I was a little bit confused.
Yeah, so it's done basically in a two-step process that's similar to the process that Bloneries and others have advocated for with randomized experiments, which is like the researchers, like you take like say Zacconi's model, or you take a full model, you estimate that, or the model itself includes a certain number of covariates, right? Those covariates are the only things that are penalized. Those are selected out by the adaptive lasso. And after those are selected out, the model is re-estimated with everything in it, you know, the treatment, the treatment variable, the forcing variable, the interaction between them, but with that modified covariate set. And then that's the final treatment effect estimate. That's where that comes from.
So it is using the penalized variables using your treatment. It's just restricting it not to penalize that.
Exactly. Treatment. It's only the constrained optimization problem is restricted only to the covariates, right? So the other variables are just they're basically set at penalty values to 0.
Okay.
So that's by design.
So that's great. That really helps. One thing about lasso and other flexible techniques that we might think about is possibilities of overfitting. Is there something that you've included in the procedure to try to address that?
In terms of, so can you maybe?
Well, we might think that, you know, the fact that we're throwing out particular covariates before showing our analysis on the basis of mean squared error in the first stage could be particular to the sample that we have or something like that. And so we're overly confident in our model results because we tossed out variables that were increasing our mean squared error and then reporting a smaller coefficient at the end of the day on the basis of the same data where we were minimizing the error. So like, to me, it's sort of like pretty clear that the standard error should go down. You're kind of encouraging that to happen in the first stage. Right. And then you're reporting that as an advantage of the model, but it could be a disadvantage too, if we think about the possibility that we're just fitting the noise.
I could see why. I guess it would be a disadvantage if it was more likely to result in more false positive results, I would say. I don't think that's the case. I think from my perspective, at least the advantage of the method is that it gives you a target for selecting covariates, and the target is, you know, decreasing that variance, right? Although I do understand what you're saying. Is that what you're thinking along the lines of, like, maybe that the decrease, like assuming that the treatment effect stays fixed, right?
Yeah, well,
variance what might increase the type 1 error or something like that?
There's a similar criticism made of optimal bandwidth selection procedures, right? So you're basically maximizing the probability that you get an effect by allowing the computer to look across a wide variety of possible settings and find the minimal one. Yeah. And the way you can address that is by, and I know Titchenik and other people do this, is they do some sort of out of sample prediction or some sort of cross-fold validation, or there's a wide variety of technologies that are available, but it's sort of like any machine learning problem would have this feature to it, and I didn't see that part of the conversation.
Right. Yeah. No. It's that's a good point. I mean, that's something that I haven't really considered yet, but that's something I will consider, especially when I mean, one of the things I did kind of think about was this idea of the problem of the type 1 error problem, you know, when it comes to the treatment effect estimation. And yeah, I mean, that's something I need to explore more for sure.
I mean, I'm sure more statistically minded people would go more in this direction, but like, you know, what are the standard errors after this procedure like supposed to look like? It's not obvious to me what that thing is that we're identifying at the end of the day with that, that estimation.
No, I understand. So those results were actually derived. Well, they weren't derived in the RDD context for sure, and I have not written out the kind of equations for that as of yet, but they were like those those kind of adjusted like those adjusted treatment effects were derived in the randomization, in the kind of like random experiment context by Blonares and Wager. And so those results are available. I mean, you know, conceptually what it looks like is, yeah, I mean, I guess conceptually it seems kind of, I guess it's just basically standard errors that, you tend to have a smaller overall variance, right? A smaller sigma, right? But of course that's not keeping other things constant. So yeah, that's an interesting point.
Following up on Robert's point on the overfitting,
Yeah.
if you're interested in establishing valid confidence intervals, at least asymptotically, but I'm not sure this is the right place for asymptotics, but like if it is, using the same data to select your model and then fit it will induce some sort of overfitting that will lead to slightly more conservative standard errors than you want. And that can even persist asymptotically depending on the underlying function that you're estimating.
Right.
One way around that is just to put your foot down and make a sparsity assumption, which gets rid of it, but that sort of gets rid of it by assuming it away. One other possibility is looking along with the Bloniers and Wager, which I've seen, but a while ago. Also looking at the Bologna and Chernizukov, the post-double selection approaches, and adapting that here, where what you do is you'd model the forcing variable, because really we're using controls to soak up variance so that we can estimate a treatment effect orthogonal to them, right? So one of the things you could do is actually run something like the adaptive lasso, or run the adaptive lasso on the forcing variable and on the outcome, and pool the selected covariates in a control in the model that you have. And something like that, because it's always an issue, because your model has your selection model has the outcome and the treatment touching each other. And you don't want the outcome and treatment touching each other in the selection phase and the estimation phase.
I see.
And that's one of the pathways that you get the overfitting in.
That's interesting. What was the paper, the Chernizukov and
Bologna, Belloni.
Okay.
And it's post double selection where they do something. They have their own variant of the lasso. But the idea is if you have a consistent estimate of these covariates, and then you can pool them back together. One other possible thought is incorporating the weights into the regression estimate, as so that you're upweighting the observations closer to the bandwidth. Sorry, closer to the cut point.
Incorporating the weights. Which weights?
Were you fitting the regression weighted by how close they were to the bandwidth, how close they were to the cut point, or not?
No.
Because you don't want to waste energy. You don't want to waste information in your data modeling relationships that are far from the cut point. There's precisely one point that we care about.
Yes. So yeah, no, go ahead.
Sorry, with an infinitude of data, you'd split your data into thirds, get a consistent estimate of the weights for how close you are to the threshold off one data, plug that into the adaptive lasso, partial the covariates out, take the covariates you select, come down to the third data set, and estimate it once under the weights and selected variables up above. But I understand with 20 observations, we're talking, like that doesn't make sense.
Right.
But possibly a finite sample approach, just doing that in one pass of the data might give reasonable finite sample results. And the last step is the last thought is to look at some form of resampling for inference rather than standard errors.
Right. Like bootstrapping?
Bootstrapping, permutation test, something.
Interesting. Yeah, I'll certainly consider both of those. Both of those suggestions. Thank you.
Oh, absolutely.
I have a quick question.
Yes.
So how do you extend your framework into fuzzy RDD?
I'm sorry, could you repeat that?
how do you extend your your methodology to fuzzy RDD?
Oh, into fuzzy RDD. I'm not even touching that. That is a very good question, though. But I think there are other people who've kind of touched upon that in a better way than I can. So, in a better way than I have. There are papers. So, like fuzzy RDD, as you know, is basically like instrumental variables, right? So there are papers that I mean, regular RDD is similar in many ways too, but there are papers where I think where regularization has been used to select out covariates for instrumental variables designs. Well, it was kind of weird, both to select covariates and to select the instruments themselves. I'm not that familiar with that literature, so I couldn't tell you exactly, what their argument is. But I think probably looking somewhere around that literature would be a good place to start for trying to figure out, in the case of fuzzy RDDs, what kind of method we should apply or how we should implement it. So yeah, that's a good point. It's just not something I'm touching.
Yeah, thank you. Thank you.
All right, any other questions? All right, cool. Well, oh yeah, Robert.
Thank you for organizing.
Oh yeah, no, my pleasure. It was really great meeting everyone and seeing Marc again. I really enjoyed these papers, and yeah, thanks so much for participating. This is a cool little experiment that I think went pretty well. So thanks so much, guys, and have a great rest of your day.
Thank you for organizing this. This was really
My
fantastic.
pleasure.
Thank
All
you.
right, be safe,
Okay.
everybody.
Thanks a lot. Bye.
Bye.